Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello everyone. In this problem, we're trying to determine the magnitude of the net force acting on a charged particle. Well, where are the forces arising from? Well, we're given that we have a magnetic field heading in a particular direction. In this case, we'll say it's up. And we also have an electric field that is headed in the same direction as that magnetic field. We're also told that the charged particle in question is heading perpendicular to both of these. So I'm just going to draw it heading to the right this way. That vector is going to represent the velocity of this charge, and that charge will be given, the amount of charge that this charge has will be given by Q naught. Right, so since this charge is heading to the right and the fields are both heading up, we have 90 degrees between the velocity vector in both of these fields. Now, what we need to do is figure out what are the individual forces acting on this charge from each of our magnetic and electric fields. So let's think about the magnetic field first. Looking at the right hand rule, if we put our pointer finger along the direction of the velocity and our middle finger along the direction of the magnetic field, we then see that our thumb points out of the screen, so that the direction of the magnetic field force acting on this charge is out of the screen. So we're going to represent that as a dot with a circle around it, and we're going to say our magnetic force direction is out of the screen. If you remember back about electric forces, the electric force acting on our charged particle is going to be given by just the charge value multiplied by the electric field value. And the direction of that electric force is going to be in the same direction as the electric field. So that electric force is heading upward. Now, since these are the only two forces acting on our charged particle, and these two forces are perpendicular, one is heading out of the page, one is heading in the plane of the page and up, these two are perpendicular, and therefore they make up the two components of the total net force acting on this charge. Another way to look at it would be to redraw the magnetic force going up, so we kind of get a side view of what's happening here. And we can draw our electric force heading to the right. It's perpendicular to a magnetic force, so the same situation we have on the left. And you can see how these two different forces add up to make the total net force acting on this object. So if we want to find the magnitude of the net force acting on our charged particle, all we have to do is take the squares of the magnitudes of each of the magnetic and electric forces, add them together, and square root. And that's going to give us a magnitude of our total net force. So what is that going to look like? The magnitude of the total net force, which is what we're looking for, is going to be the square root of the magnetic force acting on our charged particle squared plus the electric force acting on our charged particle all squared. Now, what do those look like? Let's think about what these force magnitudes are in equations. So if we want the magnitude of the magnetic force acting on this charged particle, we need the value of the charged particle, its speed, the magnitude of the magnetic field through which it's traveling, and sine of the angle between the two squared. Plus, again, we've just reviewed the force from the electric field acting on this charge is Q naught times the value of the electric field, all squared. So, real quick, let's remember that the angle between our velocity and magnetic field is 90 degrees, so that this sine of theta term will be sine of 90, and sine of 90 goes to 1. So this little term here just goes to 1, and we can simplify our equation a little bit. For 1, you'll notice we can bring out our Q naughts out of the root, so the charge is hanging out outside of our root, and we're left with V, the speed of the particle, multiplied by the magnetic field magnitude squared, plus the electric field value squared. And that is going to give us our answer. So all we have to do now is plug in the numbers we are given. For our charge value, it is 1.8 microcoulombs, so that's times 10 to the negative 6 coulombs, multiplied by the square root of a good bit of things, the velocity of this particle, which is 3.1 times 10 to the 6 meters per second. Multiply that by the value of the magnetic field. So multiply that by 1.2 times 10 to the negative 3 Teslas. And then we square that product. And then we add to that the value of the electric field squared, which is 4.6 times 10 to the 3. Oops, let me rewrite that. Times 10 to the 3 newtons per coulomb, all squared. So if we plug this into our calculator, we end up getting our answer, which is that the magnitude of the net force acting on this charged particle is around 1.1 times 10 to the negative 2 newtons.